Welcome to our BNS on Aerospace and Defense podcast series. I'm Pat Hindle, Media Director for Microwave Journal and Signal Integrity Journal. I'm joined by our hosts, Brian Goldstein, President, Analog Devices Federal, and Vice President, Aerospace and Defense Group at Analog Devices, and Sean Darcy, Senior Director of Aerospace and Defense at Infineon. Welcome, guys.
Thank you, Pat.
Hey, Pat.
And so today we have a special guest, Larry Hawkins, Director of Technical Marketing and Integrated Solutions and Systems at Richardson RFPD. Welcome, Larry.
Thank you, Pat.
So software-defined radio has been growing in popularity for many uses in the aerospace and defense applications. You know, we'd like to address some of the challenges and applications there. So Sean, why don't you kick us off?
All right, well, thanks, Pat. So welcome, Larry. So first off, we'd like to mention, due to the complexities of our last episode and Brian still being in recovery, you can't use the generic term workflow at any time during this episode.
Try not.
So the term software-defined radio, SDR, means many things to many different people. So I'd like to have us start out by having you tell us how you define it, what it means to you, and also what do you think the greater industry would consider to be an SDR?
Sean, that's a great question. SDR is a very old term. You can take it back to a long time ago when most of the radios were a super heterodyne sort of architecture made out of discrete components. Integration was limited. To be able to change a radio over a large bandwidth was difficult to be able to do. If you actually take a look at software-defined radios, you really have to look at it from an individual engineer's point of view. You have an engineer, for example, that's working on a specific application. He's thinking about that, and he wants to use that same design in his next design also, which will reduce his time to be able to work on that next design. And it's the way that it's looked at it on an individual basis. Now you have companies like Analog Devices and Infineon that try to look at multiple markets, right? You guys try to look at many different markets and try to produce parts. Software-defined radios is one of them, to be able to cover all of those different markets. But from an individual sort of engineer concept, he's interested in what he's doing now, what he may be doing in 6 months, or what he's done a year ago, and trying to take advantage of all those things. But that's the way that I look at it.
Just to add a little bit there, you know, the idea of having to redesign a signal chain over and over again for different applications is really what creates the fact that, you know, the military has to carry so many different flavors of radios now. And the idea, you know, Shangri-La is a soldier being able to carry one radio that gives him communication, gives him video, gives him data to all different points of information. And right now they're carrying lots of radio. The radio in the vehicle is different than the radio on the shoulder, which is different than the radio in the cockpit of the aircraft. And so this idea of being able to come up with common signal chains that could be change frequencies, hop frequencies, have filtering that's also tunable to move around the spectrum as the frequencies move around. I think that's a big part of what this is.
I think part of SDR, the question we could go real deep on, but we won't have time today, is how much of military waveforms and the numerous waveforms have really driven an SDR more than any other part of the market.
Well, they really do. They really drive that market. You got to look at the specifications for each one. I mean, every radio has their own specifications, and you have to be able to meet that. And it's difficult to be able to have one radio do all. And actually, if we had just one radio that did everything, we'd be out of a job. If you want to know the honest truth, because then you just design one and it works for everything, and you don't have any more design left. So
you know, they tried that with bidders, right? They tried programs to do that, and it.
You know, you talk about companies who are at the semiconductor level. Again, these are really expensive investments of a software-defined radio chip.
Mhm.
And so there aren't too many applications on their own that justify the investment.
Yeah.
So you need to make it as flexible as possible so that it can suit as many applications and markets as possible. The one market that really drives that level of investment is the commercial communications market. But the needs and requirements of that market are actually quite narrow compared to other applications, like civil and military communications applications. So to be able to understand the features that are required and make that generic product that is as broad use as possible, it's very difficult, and you need a lot of smart marketing people and applications systems people that can really understand as many of the requirements as possible. Let me follow up, and we've talked we've jumped already jumping all over the place, but software-defined radios are really accelerating in both the communications and the MILCOM spaces. And so, what are the uses also in radar and sonar and signal intelligence? How do these things impact those applications?
I again like looking at it from an individual engineer's point of view, say someone that's working on radar or sonar or EW. And I think that there's actually an SDR, you could call it an SDR used in the broader sense for most of these applications. And there's always a trade-off between, say, performance, SWaP-C. There's always trade-offs in doing these type of designs. For example, sonar. Sonar operates from 1 to 100 kilohertz. And there's plenty of ADCs and DACs that can take you directly there to between 100 and 1 kilohertz, and you are able to adjust the frequency range by doing that. And then what you're left with is an RF front end. On top of that, you're left with filtering. You're left at different power levels depending on how deep you want to go or how far you want to go from the application. And those are a little bit harder to be able to define. They change from system requirement to system requirement. The base part of that stays the same no matter what the sonar system is, if that's what you're designing. Just as an example. Now, if you take a look at something like radar, radar, Analog Devices have actually done really well just recently. They just announced a chip called Apollo, or a chipset called Apollo. And Apollo was great for software-defined radio for something like radar, because then you can take, and just to let people know, Apollo is a combination of multiple high-speed DACs and high-speed ADCs that sample up to 18 gigahertz. And or actually the RF spectrum takes you up to 18 gigahertz. It samples up to 20 gigasamples per second. And so basically you can do a S-band radar, you can do an X-band radar, and you can do all of that with one chip. So you can define that as a software-defined radio for radar applications. Now, will it cover all the requirements for every radar? No, because you still have performance versus SWaP-C. There'll be trade-offs on the baseband for it, but you do cover a lot of ground as far as software defined radars go. And if you switch over to, say, electronic warfare, right? So now you have this Apollo chip, which works for radar and other applications, but that also works for electronic warfare, because what do electronic warfare people want to do? They want to look at a very wide frequency range. And with Apollo, you can do that. You can look at a very wide frequency range. And then you want to focus. If you see something, you want to focus on a specific area. And you want to get there very quickly to be able to take a look at what that is. And Apollo is able to do that as well. But why wouldn't you want to use Apollo for every radar? It goes back to performance SWaP-C, where you have other opportunities also to be able to get there for EW. For example, ADI's Radioverse type products. You take a look, and Brian made mention of, these type of expenses to be able to do the Apollos and to be able to do the Radioverse type parts are very expensive. And the Radioverse type parts has been designed for communications, but they've made it broad enough to be able to use it for other applications. And you take that in general, where you have this this integrated transceiver, and you have something that, say, handles 500 megahertz worth of bandwidth, but you have multiple of these in one package. So you can take this transmit and receiver, and you can say cover 2 gigahertz to 2.5 gigahertz. Then you can take this other transmit and receive, and you can do 2.5 gigahertz to 3 gigahertz. And now you got a whole gigahertz worth of bandwidth without having to change the synthesizer on it, which is excellent. I mean, you can really do something. You can't do 10 gigahertz worth of bandwidth like you can in Apollo, but you can get, a gigahertz or more worth of bandwidth by using that, and just using them and lining them up side by side. Then you can flip one to another frequency. You can flip one to another frequency. And I've seen customers use that for EW applications as well. So, there's lots of ways that you can go with that. You don't also we don't have to limit our conversation to that as well. For example, you have both Analog Devices and Infineon have integrated transceivers that cover, let's say, sub-gigahertz transceivers, right? And multiple people have these sub-gigahertz transceivers, and they cover all the sub-gigahertz frequency bands below a gigahertz, sub-gigahertz, and they're very highly integrated, right? And you can use one at one frequency, or you can use one at another frequency. And I would call that software-defined radios as well, because you can use them for any one of those frequency ranges and for those applications.
Yeah, it's interesting.
That's good.
The idea of having a software-defined radio that allows you to reuse the hardware, for multiple frequency bands. But what's also interesting is being able to use the same hardware to be a radar and detect targets, to also be a communication channel, as well as to be a electronic surveillance channel. And so having the reducing the number of antennas, say, on a ship or an aircraft, is something that's an ideal scenario for a lot of our customers. And so this idea of, why don't you just design a radio or a comm system that works DC to 90 gigahertz. And so that would be an ideal world. Like Larry said, none of us would have jobs anymore, because the hardware would be done, and it would just be a software problem at that point. But the real question is, why? What are the limitations of being able to do that? Why can't we do that now? And why do we still have to break up the signal chain? And why isn't there the idea of this one piece of hardware?
I guess I would say that, the RF, the gain stage, antenna design kind of constrain the system at the RF and microwave side, as far as the analog part of it. And I think where Brian's kind of going with that is, how much of the digital and the software side can be reusable? Would you agree? And are there technologies that allow us to use a larger part of the spectrum for the SDR, both on the analog and the digital side? And how do you deal with some of those challenges? What's the Lego blocks, as I call them? Can those Lego blocks actually be quickly swapped in and out? What's your thoughts there?
Yeah, there's a lot to unpack there. A lot to unpack. If you take a look, there's a lot of system trade-offs. And when you have, a design engineer, and he's looking at specifications, he's going to say, okay, well, there's a lot of commonalities, let's say, up until the RF front end. And actually there are. there's a lot of commonalities on any one of these things up until, say, the RF front end. But now you get to the RF front end, and what do you do there? A lot of trade-offs. For example, you can look at the antenna, and yes, you can actually make a broad antenna, but a broad antenna has less gain, right?
Yeah,
So that there's trade-offs there.
correct. Yeah.
You have less gain. Now, there's certain tricks that you can play. For example, these semiconductor companies and analog devices, you do a lot to be able to take care of some of those issues. For example, you can make a narrow band antenna and switch off capacitors to be able to tune it so you can keep the gain, you can keep the narrow band, you can switch it over multiple frequency ranges, right? So there's little tricks that you can do to be able to take care of that. You take a look at amplifiers, for example, and just a broad frequency amplifier compared to a narrow frequency amplifier, and the performance isn't the same, right? And the cost is actually quite different as well.
And the current and power efficiency.
Exactly.
Oh,
And you look at efficiency, right? Let's just take that for an example. Let's talk about efficiency and what drives. So efficiency drives because of the amount of current, but that doesn't just affect the electronics. That affects the hardware around it. If you drive in a lot of current, you have a lot of heat. You have a lot of heat, you have a heat sink, and your heat sink has to be larger. So that means your system is larger, it weighs more, and it's more expensive. It's just not good.
It could require liquid cooling.
Exactly, and that adds a lot of
And
expenses.
then ultimately, are you running on a battery versus a nuclear power generator? It all matters.
All matters, but let's go down that rabbit hole a little bit further, and let's start talking about the component that drives the efficiency in all RF front ends, and that's the high power amplifier, right?
HPA, yeah.
The HPA. So you got this HPA, and if you take a look at it narrowband, it's a lot easier to be able to design a narrowband HPA over a broadband HPA. Now there's technology like GaN and so forth that you're able to do a lot better, but it's still very difficult to be able to do, a very broadband HPA. And the efficiency is affected as you try to make it broader, which hurts in all those other things, the power supply, the heat sinking, and all of those things. It makes a big difference.
So, so then when you start walking back behind the power amplifier, what else is back there? You've got the mixer, right? And, unless you're able to go directly into the converter, which is great, and that's Shangri-La as well, is that you get rid of the whole LO and mixer stage and you go right into that high-speed converter. So what's the next most important piece? It's the filtering.
The filter
Is how do you keep all the unwanted signals from getting in there and clogging up the high-speed converter.
It's not just getting in though, but it's also coming out of your system and making sure that you're not just transmitting at your specific frequency.
It's tight.
Exactly. So if you have this system where you want to be transmitting in this frequency and that frequency, but you only want to be transmitting one at a time, and you don't want to be over there when you want to be when you want to be at this frequency, then what happens if you're over there? Then you're not meeting your specifications and it's bad. And so you need filtering. So now you have tunable filters, right? Tunable filters are great. I love them, but they don't have the performance.
It's a big performance trade-off there.
Exactly. They don't have the performance of your little surface mount saw filters, right? They're not there yet.
And you need them at the front end.
Exactly.
And so
Insertion.
as you're transmitting a lot of power from your transmitter, and even the leakage into the receiver is getting back. And as these things are going through your filters, the filters don't have the insertion loss that you need at the front end behind the LNA, and they also don't have the linearity and the power handling that's required. And so that is still a technological challenge to where do you get that tunable high power, low loss filter to be at the front. And that is a critical piece of these software-defined
Right.
systems.
And there's always the ability, I mean, you can switch in different filters.
Oh, that's what they do. That
But-
is-
But it comes down to swap C, right? Size, weight, power, and if you're switching in multiple, that means you have multiple and you enlarge
That's
it, right?
Yeah.
And then you have performance, right? So it all comes back to trade-offs, which there's a ton of trade-offs
That's right.
in being able to do all of this.
Well, let me ask another question here. So let's talk a bit, we talked a bunch about the analogs. Let's jump over a bit about the digital hardware that's at the core of an SDR. So do we think that, the FPGAs, the GPUs, the CPUs are the best way to control them? What part of the signal chain are they used? And is there something where we're like maybe seeing more of an ASIC or a MMIC solution? Is that good here? And what's your thoughts on that?
Great questions. Now, I'll have to give you a little bit of a heads up. My specialty is in the analog RF, so I'm not a digital expert, but I've dealt with it. I've dealt with it a lot. And if you take a look, for example, a CPU, right? A CPU, it specializes, I should say, in taking things serial. Right, so you use a CPU when you want to do things serial. For example, you want to change the gain, and then you want to change the frequency of the synthesizer. If you look at GPUs are more serial. They're used when you want to do things at the same time. Let's say that you want to change them both at the same time, right? And you want to do a lot of other things at the same time also. Right. So that's when you want to use a GPU, and FPGAs are special because they're programmable whichever way you want to go, right? They're very programmable, and they're sort of like software-defined radios in that you can basically set them up to be able to do whatever you want. So most people start with FPGAs until they know exactly what they need to do in the system. And then once they have that, then they'll choose what they want to do after that. For example, you can do an ASIC. Now, ASICs are great. And if you have the time and if you have the overall volume, you want to go to an ASIC, because ASICs, they tend to be smaller, they tend to be lower power. You can do specifically on what you want to do with them, but they take a lot of time. And the upfront cost for being able to do an ASIC is very expensive. So if you have, let's say you only need 100 of these systems, you don't want to be paying millions of dollars for an ASIC when you can buy an FPGA to be able to do it, and the overall cost is less for the FPGA than it is for the ASIC, and you don't want to spend that time and that power there. Now, MMICs are another thing, right? But MMICs are a little bit more, they're a little bit more difficult. You have the same trade-offs between time, because it takes your time, and it also ends up being less expensive usually to be able to do a MMIC over being able to do something with individual components. But with a MMIC, usually with RF components, you have different technologies that are better for different applications. You're not just going to do it on one piece of silicon. Now you're talking about GaN, you're talking about, a lot of different gas, you're talking about a lot of different RF technology. So that they're a little bit difficult, but the trade-offs are the same there, right?
Yeah, and this is where advanced packaging comes
Correct.
in. Exactly for the reasons Larry said, is in the RF domain. You really want to mix technologies. You want GaN for power, you want gallium arsenide for RF efficiency and high frequency, and then you want silicon for low cost and digital capabilities as well. And so being able to package those technologies together, and you're going to hear a lot in the industry, and maybe we should do a show just on chiplets in advanced packaging and digital interfaces between these components. But packaging is a way of getting that flexibility of being able to work on the different process nodes while also getting the integration of not having individual surface mount components. But again, the more you integrate into a package, the less generic
Yeah,
product
you're
becomes.
specialized,
You're
right.
starting to specialize, the more complicated, the more you put in there.
That's a good point.
And so you're not getting a software-defined radio.
Right,
No,
you're walking backwards.
You're starting off, yeah, it's true. You know, you look at kind of on that point, right? A lot of people want to integrate fabric into certain things like converters or other type of components. And usually that's to offset the fact that we always look at the HPA type budget, power budget on the analog side. Think about how much power an FPGA draws, right? Especially if you have an FPGA per channel. The GPUs, great technology, right? But still not displacing FPGAs yet. Lower power, but just don't have the performance. And then back to CPUs. So it'd be kind of interesting to talk more about maybe doing a show on integration, almost from a power and a thermal standpoint.
Yeah.
You know, that kind of challenge there. So
you know, when we talk about software-defined radios, the term software pops up as much as us electrical engineers may not want to, and hardware engineers might not want to hear it. And but the fact is, as you become software-defined in nature, the skill sets needed on a design team are starting to really change, and the number of software engineers relative to hardware engineers is really starting to shift. And so, you know, as we think about these, getting into this more and more, and of course, you know, people that have been doing this for a long time understand this. And if you look up the makeup of their organizations, they're dominated by software engineers. And so it's important, even from the very minute you turn on a new component, you need software designers just to talk to it. You need software designers just to test it. And so as you're setting up these architectures, the software engineer becomes very, very important.
You know, Brian, a long time ago when I was at my first job out of college, I worked for L3 Communications, and there I was involved in projects, and with these projects, you had a time frame that you needed the projects done. And the people that weren't meeting those time frames were often called a lightning rod, because if you weren't there and done in time for the project to be done, then lightning would come. And it was often that these projects were, you know, you'd start off with the hardware, and you'd have to have the hardware before the software, right? And they'd have to have something to be able to do before they could do the software. So these guys were always starting last in the project. And so, you know, I'm the RF guy, and I finished up my stuff, and everyone finished up their stuff, and you had the software guys left. And they were the lightning rods always, and it wasn't their fault. It was because, hey, I messed up. I was slow on my part to not getting it done, and they didn't have the hardware to go on to be able to do it. And so it's really interesting that you bring that up. And I know, Sean, before we started talking here, you talked about doing it a different way. And some people are thinking maybe starting with software and then going to hardware. And I thought that was an interesting sort of concept, because as you said, Brian, the software guys always outnumbered the hardware guys, and that was usually where the slow up was, and it wasn't their fault. It was more of the hardware guys.
And that leads into a very interesting thing, because now, you know, we're being asked very early on, give me a model of your software defined radio, right? So now it's all model based. We can't have the software engineers start after the hardware is done. It doesn't make any sense. You need some of the software just to turn on the hardware. So the fact is, they need to get started earlier. And so you have this whole idea of emulators and digital twin that's getting to a point where it's expected of these software-defined radios and these digital systems that the software guys need to be able to get started and architect much earlier.
And you also have these abilities where the requirements for the non-RF front end part, the software defined radio sort of part that you can reproduce from project to project, is that stays the same. then a lot of that code stays the same as well, because a lot of that code is related to the non-RF front end
That's right.
portion of it. And that allows a lot of reuse of that software and that programming that they've done previously, which helps immensely with cutting down the time of the project.
Yeah, because the paradigm starts to change where instead of reconfiguring, rewriting your software, you now actually can reuse the software and basically modify your RF front end, right? Your gain, your filter stage, and everything else. But it is, I think, to Brian's point, I think you're seeing a demand for more models, accurate models up front, and probably a much better understanding of system engineering as a whole. Like you said, is for years, the analog guys passed the problem to the digital, who passes it to the software guys. Software always took the hit, right? There's a couple pretty catastrophic failures, but if you really looked at it, it was poor sensor design.
Yep.
Right, that really triggered the problem.
Absolutely.
Software failed, but it's because the sensors were incorrectly designed, configured, and implemented.
So let's shift just a little bit into the world specifically around communications. And so, you know, again, 4G and 5G really drove a lot of at least at the single semiconductor software-defined radio development were driven by the 4G and 5G markets. And so, you know, Larry, from your perspective, can you talk about 5G and what you're seeing in the transition to 6G? And what are you hearing on the military side? We're starting to hear a lot about the military wanting to make use of this common infrastructure, but it doesn't come perfectly easy because they do want to use other waveforms and things that aren't necessarily supported by the existing software-defined radios. And so what are your thoughts and what are you seeing on those topics?
You know, great question. And you've seen this for a while specifically, Brian, and you've been fighting this battle. As you mentioned, to be able to do these, for example, a radio verse sort of components from analog devices, right? Those were designed for your cellular communications, for your 5G, 6G. And there's a lot of investment, a lot of dollars that are brought up in that, and they're chasing these high volume markets. And then you have the military guys that see that and they say, oh, well, now we can take advantage of not only the scale, right, to be able to reduce the cost of these parts, but, you know, there's a lot of overlap now with 5G, 6G in that they're looking for a broader frequency range. They're looking for multiple of these transceivers, up-down converters in one package. And you can see that the military guys are salivating over some of these parts that can be used for their applications because they see a lot of advantages for being able to do it. And I honestly see a lot of overlap between these components and what the military guys are able to use for that, especially in communications. But there's also issues on the semiconductor side as well, right? Because now you have support issues because you're lacking support and you're looking at these high volume markets, and are you willing to be able to spend the money to be able to support someone that doesn't have quite the volume that they have, even if they can do it? Are they specifying, as you said, for the waveforms that the ADAF guys are doing and the special quirks that you need to be able to get into some of these waveforms that the military guys are doing, and is there that support? And by the way, Brian, I think your group does a great job of supporting some of those parts that are designed for the higher volume into some of these military type applications. I think you're doing a great job at trying to make that balance. But I think there's also it goes the other way as well. For example, you design a part specifically for the ADAF group, right? And you're used to using lower volume, so the price has to be higher because the volume is lower, right? You have to get back your investment that you put in. And now you have a high volume customer that says, hey, you know, we're being pushed to go wider in frequency range, and you got this really wide amplifier, and oh, but I can't spend that much for that amplifier. Can you reduce it? And I see that, the backflow on that as well. But there's quite a dynamic, and it doesn't just happen at Analog Devices, right? This is an industry-wide thing. You see parts that are designed for more of a vertical market, and then you see people with a non-vertical market that want to take advantage of some of that technology. And are they able to use that for their application? It's quite the dynamic that
That's
you see in the market.
a really interesting thing that you just said that I want to just dive a little bit deeper in is that the high volume commercial markets drive most semiconductor company investments. But truly, the DARPAs and the DoD have a vision of these technologies and the use cases for them much, much earlier. The problem is it's much, much earlier than the commercial world can afford to put the investment in. And so the DoD spends money in DoD land developing technologies that are very specific and state-of-the-art, but not scalable.
Exactly.
And so how do you connect the commercial world and the scale that comes with it with the DoD vision much earlier?
Yep.
And so that requires the commercial world to show an interest, and it requires the DoD and the government to make themselves easier to work with as a commercial company. We can have a show just on that. Because that's a very, very interesting point that you just made there. And it's absolutely right, because we are designing things for the commercial world that now we're redesigning again, because the military application is now big enough. Apollo is a perfect example. That's really ADI's first product that they've ever developed that was meant to be really broad market as a software-defined radio, really designed to be broad market with the highest performance level to suit as many applications as possible. Now, again, like you said, it's not perfect for everything because you're never going to have one size fits all. But that was the goal of that product for sure, was to make a software-defined radio that was useful for many applications as possible.
I would never use it for sonar.
Right.
Yeah. You never use it.
It's over.
Yeah.
Exactly.
Now, I guess the last thing I wouldn't mind picking your brain on 5G, 6G is how much of that do you think is driven for the need of digital bandwidth, right? A lot of modern military, modern military waveforms don't have the bandwidth. They can't pump a lot of data, right? In reality, they're 10 megabit per second. Where, you're looking at 5G ultra wide. How much do you think is actually driven by that need as well?
Honestly, if you have you have 5G, right? And there's a lot of things with this, because you're not just talking about a lot of data, you're also talking about a lot of bandwidth as well. And not necessarily because the bandwidth is necessary for a particular carrier, right? But it's because these carriers buy multiple frequency bands, and they want to be able to have all of those frequency bands in the same radio, right? Going down that software-defined radio for their application sort of thing. And then you have these Analog Devices who design these radioverse transceivers, are able to do that, are able to handle all the data that's going through. And so you have these specific chips for it. And then you have the military guys. You have some applications where you really want a lot of data, right, and you want more data than actually what the comms guys are. And then you have other applications in military where you really don't need a lot of data. And you're taking a look at the lower volume. Exactly. And it's a trade-off. But then you have the scale of these 5G, 6G, of these comms. And so it's all a trade-off. Do I want to I have a narrowband application that has very tight performance, right? Because the more narrowband you are, the more you have to worry about interfering with other people around. The tighter your requirements are for your radio. And so can they meet that requirement with their radio for your particular application. So you have to look at it specific to that. And then you have the guys that really want a lot of data in the military, right? They want that data. And these guys aren't set up for that much data going through.
That's right.
But now, can you think differently and say, hey, can I use this transmit and receive for part of it, and this one for another part, and this one for another part? And so really it's a matter of, trade-offs. And can I use one radio for all of these type of applications? And it's really something that you got to delve down individually based on your specific application to say, can I do that? And from a system engineer guy and from an overall, say, military guy, you were talking earlier, Brian, about, hey, I want to do all of this in one radio, right? Which pushes you way outside of what they're doing for comms. But luckily, these semiconductor companies have said, okay, well, I'm not just going to specify it for this specific application, but I'm going to look at how broad this will actually work and specify it for how broad these parts will actually work. And then maybe it will be useful for some of these other markets, even though I'm focusing specifically on this specific market for that. And I'd like to see more of that industry right. I think Analog Devices does a great job of that, but I'd like to see more of that industry-wide.
Okay, great conversation. Thanks you, Brian, Sean, and Larry for your insights on software-defined radios. We did touch on model-based systems engineering and digital twins, and please note that'll probably be our next episode in about a month from now. And if you have any topics you'd like us to cover, just email me at phindle@mwjournal.com. Thanks, everybody, for listening, and we'll see you in about a month.